All right, so get this. You submitted a research paper all about solar cells, right? Expecting a deep dive into clean energy, I bet. But buckle up because this one takes us on a little detour. A detour through the Cold War space race.
Sounds exciting.
Yeah, it's pretty fascinating stuff. This 1996 paper, History of Solar Cell Development in the Soviet Space Program and the Terrestrial Potential for this Technology, it reveals some surprising origins for this tech that we just kind of take for granted today.
Yeah. I mean, solar cells are everywhere now.
Exactly. And to think it all goes back to, well, competing with the Soviets to put stuff in space. We're talking solar-powered moon buggies, missions to Venus, even early attempts at solar houses.
Solar houses back then, that's
Yeah,
pretty wild.
I know, right? Okay, so before we launch into orbit, let's lay some groundwork. This paper points to a Soviet physicist, A.F. Ioffe, and his team back in the 1930s and 40s.
Ah, Ioff. His work was foundational.
Yeah, what exactly did they do that was so important for solar cell technology?
Well, Ioff was deeply into semiconductors. You know, those materials that are kind of in between conductors like copper and insulators like rubber. And his book, The Physics of Semiconductors, that was a real game changer. It was like he cracked a secret code. He figured out how light could make electricity flow in these materials. And that, my friend, is the key to solar cells.
So that's the foundation, huh? But how did we go from Ioff's lab to actually powering stuff in space?
Enter the space race. Both the US and the USSR were scrambling to get satellites up there, and those things needed a reliable power source. Batteries wouldn't cut it for long missions, so solar cells suddenly become super important.
I see the ultimate energy challenge out in the vacuum of space. So everyone's rushing to build these solar cells. Did they all go about it the same way?
Actually, no. There were some key differences in those early approaches. The US primarily went with what's called N-type silicon, while the Soviets focused on P-type silicon.
Different types of silicon. What's the difference?
Well, without getting too deep into the weeds, it has to do with how the silicon is doped, how impurities are added to change its electrical properties. It seems like a combination of factors led the Soviets to focus on P-type silicon. It was readily available, and they probably wanted to differentiate their work from the Americans.
A little scientific rivalry, huh? But wait, I remember reading something in the paper about the Soviets accidentally having a better design.
It's quite a twist. Turns out those Soviet P-type silicon cells were much tougher against space radiation. There's a book by Hans Rauschenbach that even mentions how the U.S. ended up switching to P-type silicon after they discovered the Van Allen radiation belts. Those are zones of intense radiation around Earth.
So, a lucky break for the Soviets then, huh?
You could say that, but for those of us who aren't rocket scientists, how do these silicon solar cells actually work?
Yeah, break it down for us. How does sunlight magically turn into electricity?
Okay, so imagine a silicon solar cell like a sandwich. You've got two different slices of silicon. One has a positive charge, that's the P-type, and the other has a negative charge, the N-type. When sunlight hits the cell, it knocks loose electrons in the silicon. Think of them like tiny energized balls bouncing around. The junction between those two slices of silicon acts like a one-way gate, pushing those electrons in a single direction, and boom, you've got an electric current.
Okay, I think I get it, but I'm guessing those early solar cells weren't exactly powerhouses, right?
Well, you're right. There were some challenges. One of the biggest was finding the sweet spot for what's called the PN junction, that boundary between the P-type and N-type silicon. If it's too deep, not all the sunlight gets absorbed. But if it's too shallow, you get a lot of resistance, and that saps the power output.
So they were walking a tightrope, trying to optimize that junction. How did they make those early cells more efficient?
They had to get creative. One trick was to create what's called a drift field. It's like adding a tiny electric shepherd inside the cell, guiding the electrons along, and making them more likely to reach the contacts and contribute to the power output.
A tiny electric shepherd. That's a great analogy. What else? Any other tricks up their sleeves?
They also invented what are called isotype barriers. Now, this gets a little technical, but the gist is they figured out a way to create a sort of mirror on the back of the cell. And this mirror would bounce back any stray electrons that were trying to go the wrong way, essentially recycling them to boost the cell's power.
So they're fine-tuning the design, squeezing out every bit of efficiency. But silicon isn't the only material out there, right? Did they experiment with anything else?
Oh, absolutely. One fascinating avenue was transparent solar cells.
Wait, transparent. How can something see-through generate power?
That's where things get really cool. It's all about manipulating which wavelengths of light the cell absorbs. So they made cells that were transparent to infrared radiation. That's the heat part of sunlight, but they would still absorb visible light to generate electricity. This kept the cells cooler, which was a big advantage in space where heat can be a real problem.
So less heat, better performance. Smart. Now, the paper also mentions something about two-sided solar cells. What's that all about?
Think of a satellite in orbit. It's getting sunlight from above,
Yep.
obviously, but it also gets light reflecting back up off the Earth. Two-sided cells could tap into both of those sources, essentially doubling their energy intake.
Now, that is neat. So these space-age cells were pretty advanced, but the paper also mentions using them for things like moon rovers and even exploring Venus. Those sound like stories we need to hear.
Absolutely. Those applications are where things get really interesting. Let's dive into those next.
Okay, so we've got these super efficient radiation-resistant solar cells developed by Soviet scientists, but this wasn't just some theoretical exercise, right?
Oh, definitely not.
They put this tech to the test, right?
Right. They launched it into some of the harshest environments imaginable.
The paper specifically mentioned the Venera missions to Venus and the Lunokhod moon rovers. Man, this is a tough one.
Yeah, you got that right.
Super hot, dense atmosphere.
Brutal place.
How on earth did they get solar cells to work on Venus?
Well, they knew regular solar cells they'd fry in a heartbeat, so they had to get ingenious.
Let me guess, those transparent silicon cells we talked about.
You got it.
The ones that let infrared radiation pass through?
Less heat absorption, they could actually survive.
Smart.
But they didn't stop there. They also added these special heat-reflecting coatings to further minimize the amount of heat absorbed, like giving them a sun shield.
That's some serious engineering. So these modified solar cells actually powered the Venera probes. What did those missions even do?
The Venera missions, this was a series of probes launched by the Soviets starting in the 1960s. They were the first spacecraft to land on another planet and send back data.
Seriously.
Big milestone.
I had no idea. And powered by solar cells. That's wild. What did they learn from these missions?
Oh, the Venera missions taught us a ton about Venus. The atmosphere, surface conditions, even volcanic activity. It was a huge leap forward in our understanding of our closest planetary neighbor. And, those tough solar cells, they played a crucial role.
Okay, so Venus was one extreme. What about the moon? What role did solar cells play in the Lunokhod missions?
The Lunokhod rovers, another Soviet space first robotic rovers to explore the lunar surface.
And powered by solar energy.
You guessed it.
Moon rovers cruising around on solar power, that's pretty cool. But the moon is a challenging environment too, right?
Absolutely. You've got the extreme temperature swings, scorching hot during the lunar day, bone-chilling cold during the lunar night, and of course, the constant bombardment of radiation from the sun.
Did they use the same silicon solar cells as the Venera missions?
For the moon missions, they opted for something different, gallium arsenide solar cells.
Oh.
These cells, they were chosen for their ability to handle those extreme temperatures on the lunar surface.
I see.
They're also more efficient at converting sunlight to electricity, even in those, low light conditions.
So different challenges, different solutions. But solar power was key to the Soviet space program.
Absolutely. They really pushed the boundaries of solar cell technology. And in a way, they paved the way for the more widespread use we see today. But the journey from space to Earth wasn't always smooth sailing.
Right, bringing those space-age solar cells down to Earth, things break, get dirty, wear out.
You're telling me. Suddenly they had to contend with humidity, rain, dust, temperature swings, like all these new challenges they hadn't dealt with before.
How did they adapt these solar cells to survive life on Earth?
Well, that's where things get even more interesting. Remember, this paper isn't just about space exploration. It's also about the terrestrial potential of these technologies. Let's dive into those earthly adaptations next.
Okay, so we followed these solar cells from the lab to space, tackling scorching Venus and the frigid lunar surface. But now it's time to bring them back down to Earth.
Back to reality.
Exactly. And you know what really caught my eye in this paper?
What's that?
Those early solar houses the Soviets were experimenting with. Solar houses back then, that just seems so ahead of its time.
It really does. I mean, we kind of associate the Soviet Union with, heavy industry, not exactly eco-friendly living.
Yes, smokestacks, not solar panels, right?
But these scientists, they were already envisioning a future where homes could be powered by the sun. Pretty forward thinking.
I'm picturing solar panels just plastered all over every roof. What did these early solar houses actually look like?
Unfortunately, the paper doesn't go into specific designs,
Ah, too bad.
but it does emphasize that these houses were meant to showcase the practicality of solar energy for, everyday living.
Okay, but let's be real. Were those early solar cells even powerful enough to run an entire house?
Well, they weren't as efficient as what we have today. But the paper makes a really key point. It wasn't just about, like, slapping on solar panels. It was about integrating solar power into the whole house system.
So thinking about energy efficiency from the ground up.
Exactly. And back then, homes didn't have the same energy demands as today. No endless gadgets or appliances sucking up power.
Makes sense.
By managing consumption and designing homes around solar energy, they could make it work.
That's a really interesting point. They were basically pioneering sustainable living decades ago.
Yeah, it's pretty remarkable when you think about it.
But what happened to these solar houses? Did they like inspire a solar revolution in the Soviet Union?
That's a question the paper doesn't quite answer. It mainly focuses on the solar cell technology itself,
Hmm.
but it does hint at the potential they saw. I mean, the fact that they were building and testing solar houses at all shows just how forward-thinking they were.
It does make you wonder what could have been.
Yeah.
But like you said earlier, technology doesn't always take a straight path.
Right. There are always those political, economic, social forces that can influence how innovations are adopted, even if they have the potential to change the world.
Okay, so we may not know the full story of those early solar houses, but this deep dive has still been amazing. We've seen how scientific curiosity, spurred on by the space race, led to some truly remarkable advancements in solar technology.
It's a fascinating story, and it all started with that, fundamental research into semiconductors, a field that might have seemed totally irrelevant to everyday life at the time.
Right. Who would have thought?
But as we've seen, basic research, it can have the most unexpected and far-reaching consequences.
Absolutely. It's a testament to the power of, human ingenuity, the drive to explore and push boundaries. And even though this paper is from 1996, the quest for better solar technology, it continues today.
Oh yeah, for sure. Scientists are still searching for new materials, refining designs, constantly striving to harness the sun's energy more efficiently.
This paper mentioned transparent solar cells used for something called beam splitting. Got me thinking, what if we could integrate them into, like, windows or other everyday objects, generate power without even seeing the solar cells?
Now that's a fascinating thought. It really highlights the potential for solar energy to become even more seamlessly integrated into our lives.
It's amazing to think about all the possibilities, especially knowing the journey these solar cells have already taken. From powering probes on Venus to potentially becoming an invisible part of our homes, who knows what other surprising applications are waiting to be discovered. So, to everyone listening, stay curious, keep exploring, and maybe you'll be the one to unlock the next breakthrough in solar energy. Thanks for joining us on this incredible deep dive.